Hey guys, welcome to Safi Mixed. In this video, I will drive the relation for Poisson's distribution and will talk about its properties and applications. Poisson distribution is in fact a limited case of binomial distribution. When we say that it is a limited case of binomial distribution, that means we obtain Poisson distribution under certain approximation from binomial distribution. Nevertheless, Poisson distribution is applicable to all random processes whose output ends in an integer. That is, the output of a random process when is a whole number, then we can use Poisson distribution for such random processes. For example, we measure the half-life of radioactive materials in experiments where we count the number of decays or the number of counts through Geiger counter. So obviously we are measuring the number of counts, therefore the output of those experiments are always a whole number. We use Poisson distribution because the output is a whole number. Similarly, we measure the number of photons in a beam of light of equal intensity through phototubes. Again, since we are measuring the number of photons, the output of those experiments are whole numbers. Therefore, we use Poisson distribution in such scenario. Okay, with that said, I want to first write the binomial distribution, and we know from our previous videos that the binomial distribution is given by P of n equals capital N factorial divided by small n factorial times capital N minus small n factorial, the whole multiplied with P power capital N and Q power capital N minus small n. Okay, I'll not talk about the derivation or the presentation of this relation, but would just like to describe the terms appearing here. And I would like to begin from the right side. Here, n is the total number of trials or the total number of inputs in a random processes. Small n is the number of successes out of those total number of trials. P is the probability. Remember, this is small p and this is capital P. To differentiate them, I just put a bar at the top of the P, so this is capital P. Small p is the probability of successes in a single trial. And Q, which I write it is Q equals 1 minus P, is the failure in a given trial. And then obviously capital P of n is the probability of n small n successes in this number of trials. Now I want to remove this in order to create space. And now I want to recall another relation from one of my previous videos on binomial distribution, and that's the mean of binomial distribution. The mean of successes n, which is written as small n bar, equals capital N times small p, this one p. That's the mean of the binomial distribution. I just call this equation 1 and this one equation 2. Now, in random processes, usually the total number of trials or the total inputs are very large. And we consider this n to be infinity. So this is very large. In the mathematical language, the very large is written as infinity. And when n tends to infinity, and to keep the average value of small n finite, that suggests that the small p or the probability in a single trial will be very, very small. So in mathematical language, the very, very small I write as small p tends to 0. With these assumptions, I can rewrite equation P in the form P equals the average value of the successes divided by the total number of trials. And now, if I replace this value in equation 1, I can put equation 1 again into another form, n factorial divided by small n factorial multiplied with capital N minus small n factorial, and then I put this value for small p to write it n bar divided by capital N raised to the power, oh, this is small n, this is not capital N. So I put that small n into q raised to the power n minus n. Make that correction, this is small n, not capital N. Okay, now I want to factor this thing into two factors, and that I can do by, and similarly I want to separate this 1 over n factorial from here to write it like this, capital N factorial divided by capital N minus small n factorial, and I split that into 1 over capital N raised to the power small n, and then n bar raised to the power small n, and for q I can write 1 minus n bar divided by capital N raised to the power capital N minus n. I can write it like that. Now I combine this thing with this factor to write it like n bar divided by n factorial, and I combine this with this one in the denominator to write it, I put that inside brackets, n factorial divided by capital N minus small n factorial and capital N raised to the power small n, and then I write 1 minus n divided by capital N raised to the power n minus small n. Now I call this equation 3. Remember, equation 3 is the same as equation 1, however written in different parameterization. Instead of P and Q, I have introduced this definition into it. Now, I want to evaluate equation 3 under the assumption that capital N tends to infinity. And that assumption, and to apply that assumption, we take the limit of this equation, and therefore I define a function f of n, which is obtained from the limit of capital N tends to infinity p of n, and I apply the limit to this side since this factor is independent of capital N. Therefore, I would like to write this over here, n bar divided by n factorial. I write that in a separate bracket. Then I apply the limit to this term, to this factor, and the limit to this factor, because both of these terms contains capital N. So I take limit capital N tends to infinity capital N factorial divided by capital N minus small n factorial and capital N raised to the power small n, and then limit of this capital N tends to infinity into 1 minus n bar divided by capital N into n minus small n. And I call this equation 4. Now, in order to evaluate equation 4, since we are dealing with the factorials of very large numbers, therefore it is always good to use Stirling approximation under such circumstances. So I want to evaluate each factor individually, and since I want to take the logarithm of this factor first, and for that I don't need these equations anymore, so I remove them. I will recall equation for later when I'll be substituting the values of these terms back. So for the time being, I remove them. These are not needed. And if I take the log of this factor, then I can write log of n factorial, the whole divided by capital N minus small n factorial, and then multiplied with capital this. And using the logarithm product in division formulas, I can put this into log of capital N factorial minus log of capital N minus small n factorial and minus log of capital N raised to the power small n. And using Stirling approximation, we know from Stirling approximation the log of capital N factorial equals n log of capital N minus capital N. So I can use this relation for this term, this relation for this term, and similarly I would just use the power law of log on the last term. And using this, I remove this to keep the space, but I'll use this definition. So under this definition, I can write this thing as capital N log of capital N minus capital N for this term, and then minus capital N minus small n multiplied with log of capital N minus n, and then minus capital N minus n, and then I can write that term as minus small n taking the power 2 coefficient into log of capital N. Now see, I can combine this first term with the last term by taking log of n common from these two terms, and can put this as capital N minus small n log of capital N. And I remove the brackets and multiply this minus sign with both terms. So this will become plus and this will become minus, and I write this as capital N minus n log of capital N minus n. And when I multiply this with this, it will become plus, so this term would be just become plus n, and that will become minus small n, and I have combined that term over here. Now I missed this term, so I write that over here minus n, and I can cancel this capital N with this capital N, and then I can take this factor from these two terms common to write them as n minus n. Inside I write log capital N minus log of this thing, and I write minus n at its own place. If I take a minus common from this from these two terms, I can write this as minus capital N minus n, and it would become log of capital N minus n, and this will become minus log of capital N, and this small n is its own place. And now I can convert this into division. So I can write minus n into log of capital N minus n divided capital N, or I just write this in the form 1 minus n divided by capital N log of this thing minus n. So I just removed this equation, but I'll recall it back when I'll be putting the values. So I just put this over here, remove this from here. And now I use the series expansion of logarithm, and I just write this as n minus n at its own place, and the series expansion of this is, in fact, if you recall, this is minus n divided by n minus 1 divided by 2 n divided by capital N squared and minus so on, and then this minus at its own place. So I'm writing just the first two terms of the series expansion of this thing. Now I want to separate the two terms inside this bracket to write them. I first write this term, so minus with minus will make it as minus n multiplied with this whole thing minus n divided by capital N minus half into n divided by capital N squared minus so on, and then minus into minus plus, and this is small n, and again minus n divided by capital N minus half into n divided by capital N whole squared minus so on, and I'm writing that minus n at this position. Okay, I can extract the first term from this by multiplying this to write it as this with this cancels and minus with minus plus, so I just extract the plus n, and then I write minus capital N, and the rest of the series I'm writing as it is half into n divided by capital N whole square plus n into minus n capital N minus half n divided by n squared minus so on, and this minus n over here. Now see, we have a very good form of the expression. If I apply the limit from here, capital N tends to infinity, then I'll apply the limit on each term in this equation. This thing cancels with this one, and inside this term we have a capital N, because when I multiplied this with this, the square will cancel, but I would have a 1n in the denominator over here. And I think I made a mistake. This is a series plus and so on, so this is a series and I put the plus over here. So every term carries a capital N in the denominator, and if I apply this limit, so that would go to 0. So this term goes to 0, and the same is true about this term, because every term inside the brackets carries a capital N in its denominator, and the limit would set every terms to 0. Therefore, the net result of this is 0. That means I don't need any of these things now, so I remove them and I just write the result. That means that limit capital N tends to infinity log of n factorial divided by this thing is equal to 0. And if I exponentiate this relation, I'll get n factorial limit n tends to infinity n minus n whole factorial into n power n equals, the exponent 0 is 1. So the second factor in equation 4 is in fact equal to 1. Now remember this thing, I call this equation 5, and I'll substitute this value in equation 4 later. So I just remove this, and now I want to evaluate the third factor in equation 4. And the third factor in equation 4 is this thing, limit n tends to infinity 1 minus power n minus n. And I can simplify this thing by using binomial expansion or binomial theorem. And according to binomial theorem, this thing equals 1 minus n minus n, n factorial capital N divided by 1 factorial plus n minus n into n minus n minus 1 divided by 2 factorial into n average divided by capital N squared, and so on. Okay, I can manipulate this relation to write this in the form 1, and when I multiply this in with this term, this will cancel, and from this term I'll get minus n average divided by 1 factorial. And similarly, when I open these brackets, I'll get one term like n into n squared, and that n squared, if I multiply it with this term, so the n squared would cancel with this n squared, and I'll get a term like n bar squared divided by 2 factorial, and so on. If I keep on calculating, I'll get something like this, and then I will get the term corresponding to the small n, and that small n would give me this minus n into this. So I'll write this as minus n into n average divided by n. And similarly, I can write a term for this. And from this, if I open this up, I can write this 1 over 2 factorial into capital N squared into n squared minus n plus 1. Let me check. Am I write this correctly? No, there is no square on this. So I would have this, and then I would have n divided by capital N the whole square, n plus so on. So I get two different series, or this minus multiplied with this minus will make it plus. So I have two different series, and if now I apply the limit to this term and to this term, so every term inside this term, this whole term contains capital N and its denominator. Therefore, when I apply this limit, this whole term would go to 0 there. So I ignore that, and from here I get 1 minus n 1 factorial plus n bar squared divided by 2 factorial, and so on. And this in fact is this thing minus n bar power k divided by k factorial, which is in fact the exponent of minus n bar. So I call this equation 6. Now, if I put the values of the two terms from equation 5 and equation 6 into equation 4, I would write the function. This is the output of equation 4. I can show you equation 4 on the screen. So that is equation 4. I need to write the first term as n bar raised to the power n divided by small n factorial. Then the second factor we set from equation 5 to 1, I write that value, and the third factor we get this, so this is minus n bar. Or in simplified form, I write n bar raised to the power small n divided by n factorial exponent minus n bar, and I call this equation 7. Equation 7 is in fact the mathematical form of Poisson's distribution, and you see it is nicely characterized by the mean of the binomial distribution, because n we use was the mean of binomial distribution, which happens to be the mean of Poisson distribution as well. And this dependency on the mean value of small m in fact reflects that the Poisson distribution gives a nice result, a very good interpretable result for random variables that are characterized by a uniform or by a well-defined mean. And to visualize its behavior, I want to plot this relation, that is equation 7, against n for different values of the mean, and I set the values to 0.1 to 1 to 5 and to 10, and I do that in Mathematica. So you see the plot over here. You see that the peak of each curve happens at the mean value, that is n bar, and the width increases as the mean value n increases in the plot. So a widened distribution means that is the average or the mean of the distribution is large, and a less wide graph means that the mean is smaller. From that is just a rough estimation of the mean value of the plot of the Poisson distribution. At the end, if you haven't yet subscribed to Safi Makes, kindly support the channel by pressing the subscribe button and also the like button in the video. Thanks for watching.